So let's recap now about what we have here. We have the channel gains, both direct and indirect, from each transmitter to each other receiver. And these values we've included here for reference. We have the noise powers at each of the receivers. And so we'll set an initial transmit power, and we'll set each of them initially to be at 2 milliwatts. Now, this is a parameter that would be given to you in the algorithm to sort of start it running, but in reality, it's something that your phone would just start with just to get it going in the algorithm. So the first thing that we have to do is find the initial signal to interference ratios. So then we can move on to the first iteration to compute the updated power levels and then recompute the signal to interference ratios and so on. So we'll do that now, starting with the first link A. Link A has a direct gain of 0.9 and a transmit power of 0.2. So we know that the signal, and again, remember that the signal interference ratio is signal over interference plus the noise. So the signal is 0.9 times 2 milliwatts. The first part of the indirect gain is this 0.1 here times this 2 milliwatts, which is coming from B. And then coming from C, we have 0.2 times 2 milliwatts. And then don't forget that we have to add the noise in the receiver. So if you multiply this out, you get 1.8 milliwatts on top, and on the bottom you get 0.7 milliwatts. So now notice that these are going to cancel, and so the signal interference ratio is a unitless quantity. It just tells us how much higher the signal is than the noise relative to the interference. And so if we do this out and do this division, 1.8 divided by 0.7 gives us 2.57. So now let's move on to B. So B has a direct gain of 0.8, which is lower than, again, remember the direct gain of A and C are both 0.9, but this direct gain of 0.8 times its initial transmit power of 2 milliwatts. So for here we have 0.8 times 2 milliwatts as the signal. Then the interference we have coming in from C and from A times their power levels. So we have 0.1 times 2 milliwatts plus 0.1 times 2 milliwatts. And then we want to add also the noise in the receiver, 0.2 milliwatts. So remember the noise is higher than it was for A. So in the top here then we have 1.6 milliwatts, 0.8 times 2, divided by, on the bottom we get 0.6 milliwatts. And remember, again, these guys cancel, and we do that out, we get 2.67 as the signal to interference ratio. And we can do the same thing for C. We have 0.9 times 2 as the signal. Then for the first interference, we have from A 0.2 times 2. Plus from B, we have 0.2 times 2. Plus then from C, we have plus then the noise in C is 0.3 milliwatts. Remember, that has the highest noise out of any of the receivers. And so this gives us 1.8 milliwatts divided by 1.1 milliwatt. And after we do that, we get 1.64 to be the SIR. And so just to tabulate this equation for the measured SIR, it's equal to the signal over the interference plus the noise, as we just saw. And so that's what we need to do to compute these initial SIRs.